Students, welcome back to another lecture of environmental modeling and simulation. Today we are going to discuss a very interesting topic, bifurcations. So, if you remember logistic model, which I showed you how to solve it on R using dsolve package, ODE command. Now in logistic model, let's say my n is here on y axis, time is on x axis, and k here is my carrying capacity. So if my initial n naught is quite small, I see the typical S growth, and then it plateaus until n reaches k after infinite time. What happens if I change R? So let's say I increase R a lot, where I increase R 10 times or 2 times, and I'm going to use a different color for this. Then instead of my growth looking so in dark blue, it may reach the plateau much faster. So I'm changing the R, I'm increasing the growth rate. If I slow down the growth rate, and I'm going to use another color for it, then maybe the S curve might look more flattened. In this case, I have reduced the R. Now what happens when I change the K? So let's use another color again. So let's say I keep my R same or comparable to the initial R, which was in the growth rate was in dark blue, but now I have increased the K. Now this is the new K, K dash. So my growth will be quite rapid and amazing, and then it will plateau around K dash, which is the new growth rate. So what we are seeing is that as we change the values of parameters, as long as the parameters and n remain positive, the behavior of the system does not change much. Initially there is a growth if n naught is small enough, and then the n starts plateauing or starts reaching the value of carrying capacity. If I start with n that is bigger than carrying capacity, I will see a similar behavior. There will be an initial decline in the number of n, and then eventually it will reach the carrying capacity k. Now how fast it declines in case n naught is bigger than carrying capacity, or how fast the growth is, how the growth curve looks like when n naught is smaller than carrying capacity, depends upon R, depends upon K, depends upon n naught. But the overall system behavior does not change. Now let's take another example. Now this is an example. I am a civil engineer, so I want to use a civil engineering example. So let's say I have a column. So let's say I have a column, and on top of the column I have put a load, a very heavy load. So as the load increases, I might expect some compression in the column. That might be, I can get this information by some information that I have about the strength of this material, the quality of this material, column size, height. If I keep increasing the load enough, however, this column may buckle. So it may buckle to the left, it may buckle to the right, but all of a sudden the system will stop behaving the way it was behaving before. Now under compression, there is a particular relationship that we expect between stress and strain. All my civil engineering friends, my strength of material students who have taken the basic strength of material course know what I am talking about here. By the way, stress is force by area, and strain is your displacement over overall length. So basically percentage of change you can expect in the length of the column. This behavior will no longer be the same once buckling begins. Unlike what we see in case of our typical logistic growth curves, once the load is big enough or once the column is weak enough, the behavior will change completely, the system will change. In this case, when the system changes, when I am changing a parameter, we call it bifurcation. And in this lecture, we are going to explore different kinds of bifurcation. We will also talk about when a simple logistic kind of equation, logistic growth kind of equation will undergo bifurcation. Bifurcations are extremely important in environmental models, especially when we are talking about catastrophes. So they are very important in context of catastrophes. Bifurcations are, for example, catastrophes such as an outbreak of a disease, outbreak of a pest, like insect outbreak, which is a model I am going to teach you as part of bifurcation chapter, or catastrophes like when the emperor penguins, the entire colony of emperor penguins died out. So these are catastrophes, these are sudden changes that we are seeing in our environment, in our climate, and bifurcations are very important because a system, until the parameters are within a given range, behave very predictably. The moment the parameters move out of that range, in case bifurcation is happening, we get outbreak where things blow up, values go very high, or we have catastrophes like collapse of emperor penguin colonies where species die very quickly. Okay, we are going to start with the first kind of bifurcation, which is basically the most essential bifurcation, saddle node bifurcation. Saddle node bifurcation. So saddle node bifurcation is when new fixed points either appear or disappear. So we have appearance or disappearance of new fixed points. So what is happening here is, as the range of parameters increases or decreases, new behaviors emerge. If the fixed point is stable, you have a new potential final state. If it's an unstable, then you have a different behavior of your system than what you were experiencing before. Typical example of saddle node bifurcation would be our usual quadratic equation. So let's say dx by dt is equal to a plus x square. So let's look at this system. Dx by dt is equal to a plus x square, and let's try to understand how saddle node bifurcation works. So what we are going to do is we are going to assume that a is positive. So when a is positive, let's plot dx by dt on y-axis, let's plot x on x-axis. Since a is positive, x square is equal to plus minus under root minus a, which is an imaginary solution, not x square, x, which is an imaginary solution. So what's happening here is that real solutions to this problem do not exist. So your curve will look like this. So if I try to understand how the system is behaving, notice that there are no fixed points. Also notice that dx by dt is always positive, which means that no matter where I am starting from, let us say my initial x naught is negative. Since dx by dt is positive, the flow will be towards right. If my initial x naught is positive, since dx by dt is positive, the flow will still be towards right. Okay, now let's start changing the parameter, because bifurcation is all about changing the parameter and seeing how the system behaves. So now let's slowly reduce the a and bring it close to 0. So x on x-axis, dx by dt on y-axis, we are drawing phase portraits. When a is equal to 0, our system basically collapses not collapses, our system practically becomes this, dx by dt is equal to x square, and lo and behold we have our first fixed point. This is the critical point. It is a critical point because this is the situation when a was equal to 0, when this parameter became 0, when the first fixed point appeared. Remember, saddle node is all about appearance and disappearances of fixed points. So what's happening here? Let's say I'm starting on left side of x-axis. So this is negative x, initial value of x is negative, dx by dt is positive, which means x is going to increase, the flow is going to be towards right. Very good. So I know that on left side of this particular fixed point, this fixed point is stable. It is an attractor. Let's see what happens on the right side of this fixed point. I hope students you remember that to show stability, we color the inside of the circle to like so, and to show instability we leave it void. I encourage you to draw this and solve it along with me. Just listening is not sufficient. You might be like, oh, this is very simple, but only when you start scribbling on your notepad or on your notebook will these concepts become more accessible to you. Okay, what happens when the initial x naught is positive, bigger than 0? Dx by dt is still positive, so x is going to continue increasing. The flow is again towards right side. You see, on the right side of this fixed point is unstable. So we have a situation where we have a half stable and half unstable fixed point. Alrighty, let's keep changing a. Now we are going to reduce a even more until it becomes negative. X on x axis, dx by dt on y axis, and a is less than 0 here. Now this is the first time that you will get two distinct fixed points. One of them will be positive, one of them will be negative. Let's try to understand the stability of the system, of these two fixed points in the system. So let's call it fixed point 1, which is the negative one, fixed point 2, which is the positive one. Fixed point 1, on left side dx by dt is positive, the curve is above x axis, the flow is towards right. Since dx by dt is positive, which means x is increasing, the x is going to move towards plus infinity. Between the two fixed points, dx by dt is negative, which means x is going to reduce and the flow is going to be towards minus infinity, x is going to decrease. Towards the right side of the second fixed point, dx by dt is once again positive, which means x is going to increase and the flow is going to be towards plus infinity. We can see very clearly the first fixed point is a stable fixed point. It is an attractor. The second fixed point is an unstable fixed point. It's a repeller. So notice what's happening in this system. It's a very simple quadratic kind of system, quadratic system. As long as a is greater than 0, in this particular interval, there are no fixed point, x is always increasing. As a starts reducing, fixed point appears. This is a critical situation where first one fixed point appears and then we see two fixed points. The negative fixed point in this particular case is stable and here it is unstable, the positive fixed point. So what we are seeing is as long as a is less than 0, depending upon where the system is starting, what the initial value of x is, there are two possibilities. One is that x reaches the first fixed point value here, and the other possibility is that x reaches plus infinity. These are the only two solutions, but as the value of a increases, these two fixed points collapse to each other, and as a starts reducing, the fixed points collapse into each other and eventually there is no fixed point left, which means there is no possibility that x will ever have a finite solution or x will ever reach a finite value as time progresses to infinity. Because a is bigger than 0, finally the x will reach plus infinity. So the behavior of the system has changed. This is an example of saddle node bifurcation because new fixed points, these are the new fixed points, they appeared. Now if we start actually with a negative value of a and then we increase a to a positive value through 0, we will say that the fixed points disappeared. That's why when we define saddle node bifurcation, we talk about either the disappearance or the appearance of fixed points. There are various names of saddle node bifurcation. One of the most poetic names is blue sky bifurcation because of the phrase in English that fixed points appear out of blue sky. Another is fold bifurcation, and there are several other names that I am not remembering right now, but you can look it up. The most popularly used name is saddle node bifurcation. Alright, now let us take a look at how we can see the behavior of saddle node bifurcation without having to draw 3 different plots. So here we have 3 different plots for different values of a. Let us say we had multiple parameters, then you will have to draw a much larger number of diagrams. So in order to understand saddle node bifurcation in a single plot, what we like to draw is how the fixed points are changing as the given parameter changes. So in our case here, the parameter is a, which is changing. So we plot because it is what we are changing and the fixed points are dependent upon the value of parameter a. X axis we will draw a and on y axis we will draw fixed point. Now I am making this x slightly different to show that this is fixed points, which is not same as small letter x. Okay, when a is greater than 0, we have no fixed point. So in the first and fourth quadrant, we have nothing showing up, no fixed point. When a is equal to 0, we have one fixed point and that fixed point is equal to 0. And then as a reduces, we get 2 fixed points and I am going to use a different color for that. We get 2 fixed points and they change like so, because remember our system is dx by dt is equal to a plus x square. To find the fixed points, make this equal to 0. So, x is equal to plus minus under root minus a, and when a is less than 0, we get two fixed points. One is this one and the other is this one. What we noticed in the previous slide was that the negative fixed point will be stable, the positive fixed point will be unstable. What we can notice here is that this won't be a straight line, this will be a curve, because x is equal to under root of something. Now, negative 1 is going to be stable, so I can show the stability of this particular fixed point using a line, and in the contrast, to show unstable fixed point, the positive one is an unstable fixed point, we use a dashed line. In your exam, I'll ask you to draw all these diagrams to show me the behavior, and to look, if you just look at this, there are no fixed points in the first and fourth quadrant, and then when a becomes less than 0, two new fixed points appear. One of them is stable and one of them is unstable. Okay, now let us take a look at another example of saddle node bifurcation, and we are going to use geometric approach for it. So, our system now that we are going to look at is dx by dt is equal to a minus x minus e to the power minus x. So, we have one parameter, clearly this is the parameter that we are going to vary, and we are going to see how the system behaves, and we have two terms here that do not have the parameter. So, it is going to make our life little easy. Now, analytically, if you are trying to do this on paper, finding fixed points for this system is going to be very hard, because you have to find out for what value of a, for what value of x will this system be 0. So, we are not going to try to do it analytically, like in the previous case we did do it analytically here. So, in this case we are going to use geometric approach even for finding the fixed points. We have gone through this before, so I hope you remember. Let us plot dx by dt on y-axis and x on x-axis. What we can do is we can split our dx by dt very conveniently into two different functions. The first function we can say is a minus x, which is a simple line with negative slope. The second function we can say is e to the power minus x, which is a curve, which is quite easy to draw. And what dx by dt basically is a subtraction of these two functions. When dx by dt, when the line is above the curve, dx by dt will be positive. When the line is below the curve, dx by dt will be negative. When the line intersects the curve, that is our fixed point, because that is when dx by dt will be equal to 0. Alright, let us draw the line. So, we are going to assume a is positive, a is the intercept, minus 1 is the slope of the line. So, our line looks like this. Now, let us draw the curve e to the power minus x. When x is equal to 0, here e to the power minus x will be equal to 1, like so. As x goes negative here in this direction, this will increase exponentially. So, we are going to see a curve like this. As x increases in the positive direction, so if x is positive and we are increasing, this will become closer and closer to 0. So, this is how e to the power minus x curves look like. Now, notice here a is positive. I have also assumed that a is greater than 1, because here is 1, right? And what I am noticing is that there are very two clear fixed points. These fixed points are where the two functions 1 and 2 intersect. So, let us call this fixed point A and this fixed point B, and let us look at their stability. Now, notice on the left side of fixed point A, so if our starting value is somewhere here, the line is below the curve. Function 1 is below the curve, which means 1 minus 2, function 1 minus function 2 will be less than 0, which means dx by dt will be less than 0, which means x is going to reduce. So, we are talking about the flow moving towards the minus infinity. I should remove this sign here, not to confuse it with the flow. Now between the fixed points A and B, the line is above the curve. The line is above the curve, which means 1 minus 2 is going to be positive, the line minus curve is going to be positive, so dx by dt is positive, which means x is going to increase, so the flow is going to be towards right side. On the right side of fixed point B, once again the line is below the curve, which means again dx by dt is going to be negative and the flow is going to be towards left side. So now by looking at the arrows which are denoting the flow, you can tell A is unstable fixed point and B is a stable fixed point. Okay. This is a very simple phase portrait when A is greater than 0, and not only that, when A is greater than 1. Now let us reduce the value of A. Let us reduce the value of A. So what we are doing is basically we are reducing this intercept, we are bringing the line down. So as you bring the line down, this is still e minus x, this is dx by dt, and this is x. As you bring the line down, there will come a time when this line no longer intersects. So the fixed points have disappeared. There will also come a time when the line will be perfectly tangential to the curve, which means there will also come a time when the line will be tangential to the curve, when a minus x will be equal to e minus x for a given value of a. So what we need to do is we need to find that a critical. At what value of a is the line tangential to the curve, and how does the stability of that particular point looks like when they do meet. So since 1 and 2, the line 1 and the curve 2 are going to be tangential, two conditions are going to be met. The first condition is that they will have exactly the same value, which means a minus x, this is condition, the first condition, a minus x will be equal to e to the power minus x. The second condition would be that their slopes would be same. Slopes here in this phase portrait. So we are differentiating with x. So when you differentiate, what we will get is minus 1 is equal to minus e minus x, which means x is equal to 0. So when the line is tangential to the curve, it will look like this. And this is also the reason why I did not draw it earlier. Like so, right? Now what will be the value of a for them to be tangential? You need to put this value in the first condition. So you will get a minus 0 is equal to 1. So a critical is equal to 1. For this value of parameter x equal to 0 is where the two curves meet, where the fixed point will be. So we still do not know how this equation looks like if we are trying to plot dx by dt versus x, but we do know how fixed points behave. First there were two fixed points, the smaller one was unstable, the positive one was stable, and then when we reduced a sufficiently, there came a time when the two fixed points met each other, and now we are going to figure out, and this is the situation, and that happened at a critical of 1. At this particular value, on the left side of this particular fixed point, the line is below the curve, which means dx by dt is going to be negative, so the flow is going to be towards minus infinity. On right side of this curve, the line is still negative, which means the flow is going to be towards minus infinity. So on the right side, this is a stable fixed point, and on left side it is a unstable fixed point. So notice what is happening, the fixed points are collapsing into each other and then they are disappearing. So again, this is the case of disappearance of a particular fixed point, this is a case of saddle node bifurcation. So now let us draw a single diagram that summarizes the saddle node bifurcation. On x axis we are going to plot the parameter a, on y axis we are going to plot the fixed points. not to be confused with x. Notice when a is equal to 1, there is only one fixed point. So, at a equal to 1, there is only one fixed point, and it is half stable, half unstable. And then when a is greater than 1, there are two fixed points. So, at a greater than 1, we will have two fixed points. This is a equal to 1, a critical. And if you look at the two fixed points, the negative one is unstable and the positive one is stable. So, the negative fixed point is going to be an unstable fixed point. The positive fixed point is going to be a stable fixed point. So, this is how our diagram looks like, our parameter versus fixed point diagram. Notice again, when a is less than 1, there are no fixed points. When a is equal to 1, there is one fixed point, half stable, half unstable. When a is greater than 1, we have two fixed points. One is unstable, one is stable. This is the classic example of saddle node bifurcation. In the next lecture, we are going to talk about transcritical bifurcations, which are fascinating bifurcations in which the system have indestructible fixed point. For example, for most of the growth models, we know that when the initial number of organism is 0, that is a fixed point. It is an unstable fixed point, but it is a fixed point. No matter how the parameters change, that will always be the case. Something will not be born out of nothing. So, that we are going to study in the next lecture. Thank you very much.